So one of the special things that happens when we look at like the radius, diameter, and a chord all inside the same circle is that if we draw the radius or diameter so that it's perpendicular to the chord, it'll automatically bisect that chord. Okay, and we can say the same thing in reverse. If we draw it so that it bisects, it's automatically perpendicular. But most of the time we use it this way, where we draw the radius or the diameter perpendicular to the chord, and it automatically bisects that chord. Okay. For example, here it says find each value. And for our purposes, we're going to find the length of the chord. So I want to find the length of the entire chord. And I would also like to find the length of the radius for this one. Okay, so those are the two things I want to find. And really, we're going to use both of the things that kind of happen in this special scenario, the fact that it bisects and the fact that it's perpendicular. And so starting with the fact that this thing bisects this guy, so right here I've got a radius that's perpendicular to this chord down here, okay? And so if that's perpendicular, it means it bisects the chord. In other words, if one part of the chord is 7 centimeters, well, then this other part of the chord over here must also be 7 centimeters, okay? And so that idea that the radius is bisecting the chord just tells us, hey, if one side is 7, the other side's 7. So those two pieces are equal, which now means that the entire chord, if the one side is 7, the other side is 7, the entire chord is 14 centimeters. Okay, and that's just going back to segment addition. The two parts add up to the whole thing. So the chord is 14 centimeters long. But now let's talk about the radius. I have part of the radius. Notice I have just a piece of the radius at 3 centimeters, but I want the entire radius. In other words, what's this little piece down here? And the thing that's tricky is I can't literally just find that little piece, okay? There's no way for me to do that. What I have to do is I have to draw a different radius, okay? The radius that's drawn, I can't really find anything using the radius that I already have drawn. I have to draw another radius. And so here's the thing. We have to be strategic. Like I could draw a radius like this, or I could draw a radius that goes like this to make a diameter, or one like this, but none of those help me. The radius that helps me is when I draw the radius that goes right here, that goes from the center to where the end point of this chord is, because this creates a right triangle, okay? And anytime we're dealing with right angles, right triangles typically help us find values. And so let me kind of zoom in on that triangle. I always like to draw things off to the side, make them a little bigger. When I zoom in that triangle, we got 7 centimeters down here. We've got 3 centimeters over here, and we've got a right angle here. And this guy over here, let me highlight it in green. That was this guy right here. That's the radius, okay? And so what I can do is I can find the radius simply by doing my Pythagorean theorem. And so for this one, the radius is the hypotenuse. So when I do the Pythagorean theorem, a squared plus b squared equals c squared, or in this case, r squared, the radius squared. And so I simplify. And to solve this thing, I take the square root. If I take that square root on my calculator, I get a 7.6. So the radius is 7.6 centimeters, okay? And so once again, when I see right angles, I can form right triangles in order to find missing pieces, okay? If I look at the next one, kind of going the opposite way, here I have the entire chord. So in this one, the entire chord right here is listed as 11 inches, okay? But if I have a radius that's perpendicular to that, it's going to bisect the chord, which means it's going to split it into 2 equal pieces. So I just divide and I find out, well, one of these sides would have to be 5.5, and the other one would also have to be 5.5, okay? So it bisects that thing. So if I start with the whole thing, yeah, each piece is the same. Or if I start with the entire chord here, yeah, of course it's going to bisect. It's going to split this into 2 equal pieces. I just have to divide. So in this one, x equals the 5.5, okay? So kind of just doing reverse of what we did in the previous one with the chord. In the previous one, I had one of the pieces, and then I could use that to find the whole thing. Here I had the whole thing. It bisects to find the pieces, okay? If I look at this one, it says find the length of the chord, and once again, this time I have the radius, so here I have the radius drawn. I have this little piece over here drawn. What I'm missing is this guy right here, okay? And once again, if I kind of zoom in on this thing and kind of take it off to the side, it looks like this, where this is 10 feet, over here is 6 feet. So I'm missing this side over here. Well, I'll call it B. And once again, it's just creating a right triangle and using the Pythagorean theorem to solve this thing. So for this one, it's going to be b squared plus 6 squared equals 10 squared, or 6 squared plus b squared equals 10 squared. The important one is the 10. And now I solve this one. That's a 36. That's a 100. I have to subtract the 36. And then once again, I take the square root of this thing. So I find out that b equals 8. In other words, this little piece, and keep in mind that that is not the entire chord. That's only part of the chord. This little piece of the chord is 8 feet. But since it's being bisected, the other side has to be 8 feet, meaning that the entire chord, well, that's got to be 16 feet. Okay? So once again, the chord is being bisected when we draw that radius or that diameter perpendicular to this. So there's two things that happen here. Bisecting allows us to find some of those pieces of the chord pretty easily, but the fact that it's perpendicular allows me to set up right triangles and solve using my Pythagorean theorem.